Hi there, Matt Roscoe from our Math 301 course teaching mathematics with technology for teachers. Um, this is just a short video to introduce you to Project 2 in my absence. So I went ahead and pulled up the project statement. Let's go ahead and start there, and I'll fit it to width so we can read a little bit better. So the project is due November 8th, and it's about supporting IBL with DGS. So here's a quote from Wikipedia. Inquiry-based learning, or IBL, is primarily a pedagogical method developed during the discovery learning movement in the 1960s as a response to traditional forms of instruction where people were required to memorize information from instructional materials, such as direct instruction or rote learning. So the philosophy of inquiry-based learning finds its antecedents in the constructivist learning theories, such as the work of Jean Piaget, John Dewey, Lev Vygotsky, and Paulo Freire, among others. It can be considered a constructivist philosophy. So specific learning processes that people engage in during inquiry learning include questioning, creating questions of their own, obtaining supporting evidence to answer questions, explaining evidence, connecting explanation to the knowledge obtained from the investigative process, and then creating an argument and justification for the explanation. So that's all off a recent copy and paste from Wikipedia. I thought it was a nice introduction, so I thought, why reword it? I'll just use it. So DGS, of course, which is dynamic geometry software, that allows the teacher of geometry the opportunity to provide students with pre-made geometric objects accompanied with a series of mathematical tasks to be performed on the object that can facilitate IBL approaches to learning math. So most DGS include features that promote this approach to teaching and learning by providing things like show hide buttons, animation buttons, sliders, dynamic output of text, or dynamic coloring, or color itself. Um, so in the course, you've learned how to use DGS to construct these geometric models of objects that are commonly found in K-12 education. And your task in this project is to go ahead and create your own lesson that promotes inquiry-based learning using dynamic geometry software. So IBL for DGS, or IBL with DGS. So here are the tasks I'm going to ask you to do. First, what I want you to do is identify a Common Core state standard that's the learning target for the lesson, and give just a brief overview in paragraph form of the lesson. So what are you going to do? Just tell me briefly. And then give another paragraph that's sort of the rationale for the lesson, including sort of a clear description of how the lesson promotes IBL. And then what I want you to do is to write a lesson plan, give me a DGS applet, and some learning materials. This will be the bulk of the points. So I'll 4 points for the applet and 4 points for the lesson plan and learning materials. So write a lesson plan for the activity. I don't have a specific lesson plan format that I like. If you want it as a narrative form, you can certainly do that. There are lots of templates online that use tables or tabular forms to include how many minutes on each part. But just sort of a plan, something that you could, provide enough detail on that if you were absent, a teaching colleague could use it to replicate the activity in their classroom without asking you any questions. So what are you going to do? How are you going to run it? So a lesson plan. And then maybe in the lesson plan, some sort of an active link to a DGS applet incorporating at least 3 of the features listed above that supports the lesson. So more than just a sketch, I'd like it to have some text or maybe dynamic text. I'd like it to have some show hide buttons. The use of color might be nice. And any other materials that we needed to carry out the lesson. So if you decide you want to do it this way, but the example I'll show you will be this way, that you might have a handout that you're going to give to students to guide them through the lesson. And then the last thing I would like is some sort of an assessment plan. So, I mean, how in the world are you going to assess this? So write an assessment plan for the activity explaining how it'll be graded. And then why don't you provide a sample student response to the activity and demonstrate its grading? So in other words, what are you going to get from a student? How would you, assign the points? So that's it. These 3 tasks, each with sort of a couple subtasks on there, is what I would expect in a few weeks from you as a demonstration of your ability to use DGS. Some learning targets that you might consider. There's the vertical angles theorem, triangle interior angle sum theorems, generalized interior angle sum theorem for any polygon. So for things like quadrilaterals, pentagons, hexagons, and so on. How about the exterior angle theorem for triangles, or the inscribed angle theorem, or the central angle theorem? There's this thing called Thales theorem. You could help kids understand angles created by parallel lines. How about the Pythagorean theorem? There's all of the transformations, reflections, translations, rotations. You could do right triangle trigonometry. How about the unit circle and or periodic functions? It might be sort of hedging towards functions, but I thought it would be fine to do here if you want to try it. Similarity, so similar triangles might be interesting here. How about scaling and dilation? And then all of the areas, triangles, rectangles, parallelograms, trapezoids. My daughter in 6th grade is learning these right now, and of course they're all static diagrams. And then if you're, kind of heading for pre-calculus and think you'd like to do that, both the law of sines and cosines would be nice things to explore with GeoGebra. And then there is this thing in trig where there is a trigonometric formula for the area of triangles. So 1/2 AB sine theta, I think, is the way we think of that. Where A and B are the lengths of two sides, and theta is the angle between them. So those are all things that you might consider. Of course, that's not the only things you can do. Anything works as long as it falls within, I guess, the purview of K-12 geometric education. Probably should stick to middle and high school. All right, so that's the idea. So where can I get started with a Common Core target? So I'm going to just show you that, if you want to go in and read the standards, you can quickly go to the Common Core corestandards.org/math, and here are our standards. I'm going to go to high school geometry. Of course, there are geometry standards in 6th, 7th, and 8th as well, but I'll go into the high school standards, and the one I'm going to do has to do with circles. I'm going to do the central angle theorem, which is something we talked about earlier in the course. So the idea here is apply and understand theorems about circles. And the one that I want to do, it would be this one right here. It says identify and describe relationships among inscribed angles, radii, and chord, include the relationship between central and inscribed. That's the one I want, the relationship between central and inscribed angles. So that's the target I'm going to shoot at. So what I would do is I would probably I would copy this particular standard and its I guess definition, and probably give its its Common Core code, HSG, so high school geometry, standard C, which I think stands for circles, and it's A2. And then I'd copy this text. So that would be my, I guess, my Common Core standard. And then I would give a brief overview of the lesson. I'll show you the lesson so that you can get a sense of what it's about. And then a rationale for how the lesson promotes inquiry-based learning. So where I think students are forced to really inquire or sort of do the things that Wikipedia says inquiry-based learning lessons do. So where can they create their own questions, get supporting evidence, explain it, or connect it, and create an argument. So I think you'll see that in the lesson I have written. And then what I would do then is write a lesson plan for the activity. I'm not going to do that for you. I think it would be boring for you to sit and watch me write a lesson plan, but I will show you the DGS applet that I created and the materials that I created. And I think that's probably the first thing to do, is sort of to come up with an idea of, well, what's a good applet, and then how could I use the applet, so that kids could learn the learning target. And then once I sort of have B and C, I think A is easier to write sort of at the end. So I'll do that now. And so let's see, I guess I can open up GeoGebra and show you the applet that I created. I'm working in GeoGebra Classic 5. So I'll just open recent central angle theorem. Here it comes. So this of course is in finished form. I have the algebra pane hidden from view, and so it's sort of ready to upload, I guess. I did include a slider here. So what the slider does is it controls the radius of the circle I've drawn. So what I did is I placed the slider. Sliders are available right here. I placed the slider on the text first, and then I used circle with center and radius, and then I just typed in R as my radius. So I thought it would be kind of neat to show you what a slider can do. We haven't done a lot with sliders yet, but you can control things with values, of course. So lengths can be controlled with sliders, and sliders are kind of a nice thing. What I wanted students to see is that this relationship between central and inscribed angles does not depend on the radius of the circle, so it works for any circle. I put in some text to say drag points A, B, and C and slider R to investigate how the central angle is related to the inscribed angle that subtends the same arc on the circle. This is where I use the word that sort of comes up in the statement often, this idea of subtending arcs, so belonging to the same arcs. So I did put some checkbox in so they could see the difference between the things that are called central angles. So central angle, of course, includes the center of the circle at its vertex. The inscribed angle would be the one that's on the circle. All vertices are on the circle and show and hide the subtended arc that they share. So in other words, the central and inscribed angle share the same arc or open up to the same arc. And so you can see that this angle, even though I'm changing where the vertex is, remains constant. It always appears to be about half of that angle's measure. I could change this to something, I guess, a little easier to maybe measure. I don't know, we could do sort of a 90-ish, somewhere in there, and this one's 45. So it appears that the inscribed angle is always half of the central angle's measure, no matter what configuration I put it in. I do notice that sometimes the blue angle's inside of the red angle, sometimes it's outside of the angle, and sometimes it's on, so I have to actually sort of see that. And I could sort of continue to, I guess, remind myself what these things are by showing and hiding them. And that's it. So that's the way it works. I went ahead and uploaded it to the internet. So this is what it looks like as my applet on the internet. So fairly similar to what we saw before. Basically controls the radius, show, hide. I don't think I need to show you this again, but this would be, of course, the website that I would send students to begin the investigation. Okay, so now I've created something that I want, kids to use, and this is the really tricky part. It's like, well, how? How do you? This is where you get to be really creative, thinking about, okay, if I want them to, inquire directly about this, what would I ask them to do with this? So Josh, this is really a nod to you, right? The big question is, how do we teach with this thing? How does it change things? And this is obviously not a class on pedagogy, it's a class on technology, but I think that the idea here would be to try to, ask a series of questions that would help students sort of see the relationship and come to a conjecture, and then help them to potentially prove this. And then perhaps have a couple extensions. So that to me sounds like a good one-day lesson. Interact with it, come to a conjecture, try to prove some piece of it or maybe all of it, and then maybe for homework a few extensions. So this is what I came up with. I came up with this worksheet. So let's see if I can find it. This one. There it is. Oh, I'm sorry, it's off my screen. So here's what I did. I just created a worksheet that I would hand out, and then perhaps they would have, Chromebooks or something like that. And I would say, go ahead and follow this link to the Explorer, and then use the GeoGebra Central Angle Theorem Explorer to fill in the missing angles in the table below. So if the central angle is 120, what's the inscribed? If the inscribed's 90, what's the central? I got a 220, 45, a 60, a 12, a 126. So hopefully this is sort of gets them interacting with the applet, and I guess maybe working together with a partner, checking to see if they're getting a similar thing. But hopefully this would give them a sense of what's going on, is that the inscribed angle is always going to be half of what the central angle's value is. And so what I would say down here is, let's make a conjecture. So use the information you've collected in the table to make a conjecture about the relationship between central and inscribed angles that subtend the same arc on a circle. And then I moved on here immediately into the proof part, because I think it's going to take them quite a bit of time to prove. I think the meat of the class will be here. So it turns out that if you've ever looked at the proof of the central or angle theorem, there's different methods of proving it, but the one I like the best splits the proof up into three subproofs. So I say that there are three different possible configurations that will need to be proved before we can rely on the conjecture as a theorem. And here are the three different configurations: the vertex of the central angle inside the inscribed angle, the vertex of the central angle is on a leg of the inscribed angle, and a vertex of the central angle outside of the inscribed angle. So identify which drawing below shows configurations A, B, and C. So this would be on the leg, this would be inside, so this would be A, this would be B, so that must mean this one's C. Yeah, the central angle is outside. So these are the three configurations. So in other words, the proof for this one doesn't generalize to this one or this one. We have to prove those separately. So that's the idea, that there are kind of three subproofs. So I want them first to understand that there's sort of three things that need to be proved. And that's kind of convenient here because then we can split the class up into three subgroups. I mean, I'm guessing that there's 20 kids in class or something like that, and so maybe we'd have three groups of 6 or 7 students working on each one of these independently. So I'm going to assign them to groups to prove one of the three cases above together with their group, and I'm going to ask them to work together on the whiteboard to try to determine a logical path that proves the conjecture. Record this logic below as a proof sketch. So in other words, I'm giving them a spot to give a messy proof, right? A rough draft. And a circle with centers provided for you to make an accompanying drawing. So I would assume they would draw one of these three things right here, and then there would be a whole bunch of sort of, let's just see if we can get this, right? It turns out the really important thing here is to draw in lots of isosceles triangles. So for example, if I draw on this line and I draw on this line, I get 3 isosceles triangles, which gives me base angles that are congruent and a whole bunch of triangles, angle sums. And the idea is, using some algebra, you should be able to squeeze out that this guy's half of that guy. So that's the idea, I guess, behind the proof. You might want to try it on your own if you want to know for sure. This one is a little bit harder, and sorry, this one is not any harder, but this one is definitely a little bit harder over here. So it would be interesting to see at what rate these two would get proved, and whether or not then they could provide some help to this person. So this part would be the place where the instructor is really going to have to do a lot of monitoring and helping, I guess, students get a toehold on this. So anyway, I thought that would be an interesting way to do it. Split them up into 3, assign them one of them, and make that their turn-inable assignment. So once they've kind of done that, I would assume at this end of this page, this would be probably where we might be at the end of class. So I would assume by number 4, we're done with the 50-minute period. I would assume it'd probably take them, high school student, probably take them 10 or 15 minutes to do this part, form a conjecture, just a minute or two to do this part, and then we're on to sort of 20 to 30 minutes on trying to prove this thing. If they do get it proved, well, then they can right away hop into sort of the extensions. So this would be rewrite your proof sketch as a formal proof below. Be sure to include a drawing, a hypothesis, a proof, and a summary statement. So giving them a whole page to provide a proof to one of these 3 settings. Boom, boom, boom. Hope that makes sense. And then the last thing are sort of extensions. So what does the central angle theorem say about any triangle that's inscribed on a circle in such a way that 2 of its vertices form a diameter? So here what would happen is they could perhaps go back to the applet and take a look and see what seems to happen. So how do you, basically what's going on here is that the central angle, if it's a diameter, is 180. So the inscribed angle that corresponds to that central angle is going to have to be half of 180 or 90. So anytime we construct an inscribed triangle on a circle such the way that one of its sides is a diameter, that triangle will be right. So that's what I'm hoping that they would explain. Not necessarily a proof here, but definitely an application of the inscribed or central angle theorem, and some sort of I guess, a logical argumentation there. And then the last one, probably, I thought about making this like extra credit or beyond, but there's this kind of interesting configuration on circles. I call it the bow tie figure. But you have 2 intersecting chords of a circle, one here and one there. They're used to construct 2 triangles, as in the drawing below. So intersecting chords, so those are straight lines. We get 2 triangles like this, right? And it appears, I don't know if you see this, but it appears like the two triangles are similar. They're the same shape but different size. And the question is are the triangles indeed similar? And I'm asking them to argue using the central angle theorem. It's pretty easy to see that these two angles are congruent because we've got vertical angles there. But the real difficult part is, why is this angle and this angle congruent? As soon as I know that, if those two angles are congruent and these two are congruent by vertical angles, then I know by triangle angle sum that these two are congruent. So, I mean, I have to argue that, this pair of angles are congruent. And one of the things you might have noticed is that those two angles subtend the same arc here. So since they subtend the same arc, they have the same central angle. So that means that they're half of that same central angle, even though it's not drawn. Those two angles are congruent. And that's actually another theorem. It would probably be the next theorem in line for circle theorem. It's called the inscribed angle theorem. It just says that any two angles that subtend the same arc on a circle are congruent. And it's a direct corollary of the inscribed angle, the central angle theorem. Okay, so I hope that gives you a sense of sort of my activity. I'm not going to write out, I guess, a lesson plan for it, but I showed you my materials in the DGS link. I actually haven't really thought deeply about the assessment plan. I'm going to leave that up to you to sort of, I didn't want to telegraph anything here. I mean, my guess is that I would assign point values to each one of these pieces that I collected in the worksheet. So that's basically the idea, and then I could, of course, quickly do a sample student response to the activity. I hope that I give you a good sense of what it is I'm expecting. Once again, the due date is November 8, and I look forward to seeing what I get from you all. I'll be back on Monday if there are questions about this, if anything's unclear. And you're certainly welcome to email me in the meantime if you have any questions that need to be answered. Okay, I hope you're having a great week, and I'll see you upon my return.